Alright. Set 0.
Our official weight is 47.15 kilograms. Across the front wheels, we are 58.8. And across the back wheels, we are 59. Our height is 59.2. And our length is 107.
We start out the competition with Naj from programming firing up the code for teleoperation. We used ROS2 as our robotic operating system this year. As you can see, the robot was randomly orientated at its starting position. You can also see 2 out of the 3 boulder obstacles located in front of the wooden sieve. Due to inclement weather conditions here in Utah, our choices of digging material were quite limited. The team ended up needing to use the salt barn, where the university stores its road salt that it lays down on the road when it snows. Naturally, this material provided some challenges when operating the robot, but overall worked quite well as an alternative to sand. As you can see, the robot is a 4-wheeled skid steer mobility system. The digging system that you see there in black is what we call the Archimedes drum. It is in essence a combination of a drum digger and an auger, which capitalizes on the strength of both digging systems, while limiting the non-desirable parts of both. The system was designed to be able to penetrate and have the capacity to hold material like a traditional drum digger, while not needing to pull the digging mechanism out of the ground in order to filter out excess material. As you can see, the top of the Archimedes drum is quite wide. Inside of the Archimedes drum, there is a secondary auger, which is fixed in place with respect to the rotating drum. An internal filter that allows finer particles, such as the BP1, to pass through the internal screw, which is then lifted the excess material up the arm, where it is deposited back onto the surface through holes located just below that white Delrin cap that you see at the top of the drum. This capability allows us to keep the drum submerged under the surface at the targeted depth for BP2 collection during the entirety of the mining process. As you can see from the large buildup of salt around the exterior of the drum, the size of the grains of salt and its nature to stick together because of moisture prevented us from being able to showcase this ability. This inevitably led us to operate the digging mechanism as a standard drum digger, where once the drum was full of material, we would need to pull the drum out and dump the excess material. Behind the drum digger, you can see a red steel bracket and a large motor inside of it. This Maxon motor powers the drive shaft which turns our Archimedes drum. This is an exceptionally powerful motor, providing more torque than a Toyota Celica. One of our members calculated this, and we found it to be a fascinating piece of information to include. It is currently 8:25 p.m. locally here in Utah, and that is why the arena is dark. We decided to light the arena with headlights from our cars, and the team agreed that the way the light casts on the arena truly made it feel like a lunar environment. As you can see, while we're lowering the digging mechanism, we are rotating it backwards. This allows us to force the Archimedes drum as deep into the sand as possible before we begin the excavation process. The intent behind this design was to allow for the drum to be submerged while the robot reversed, similar to how bucket ladders trench. However, the material we are digging in prevented us from being able to do this. The team thought that this capability was valuable, as it would allow us to maximize the time excavating at the desired depth. This capability is the reason why you see the large auger on top of the drum. At the optimal digging depth, the auger would be submerged and would create a downward force, providing traction to the wheels, as well as preventing the Archimedes drum from being pulled out of the dirt while the robot was reversing. The auger also worked to agitate the dirt above the drum, making it easier to pull out the digging mechanism backwards while submerged. The vertical motion of the Archimedes drum is made possible by the use of a worm gear. This particular worm gear has a gear ratio of 40:1, which was required in order to be able to lift the 25 kilogram arm. The large diameter wheels, along with directional tires, help to prevent the wheels from digging themselves in and becoming stuck, as well as aided in the skid steer turning. In previous competitions, the team noticed that small diameter wheels with skid steering often cause the wheels to be submerged into the digging material and become stuck. As can be seen here, bugs in the code led to the wheels occasionally becoming unresponsive for a short period of time. This proved not to be an issue and was resolved quickly when it did occur. It is now time for us to return to the sieve and deposit the mined material that we've collected. The competition run was cut short due to the mechanical failure of a spider shaft coupler that was connected to the Maxon motor which drove the shaft of the drum digger. If you look closely, you will see a T-shaped piece of aluminum attached to the front of the motor. This is a protective measure to ensure that the motor does not break loose and spin out of control if a failure occurs. It rests inside the steel bracket holding the motor, and you will see it quickly rotate clockwise during the point of failure. The team is grateful that it occurred during the dumping portion of the competition rather than while excavating. However, it made for an abrupt end to our competition run. Overall, the robot was a success, and the team looks forward to refining it during the rest of the semester. Thank you for watching Utah Student Robotics demonstration of the Archimedes robot.